Start recording there. Let me get my phone going. Nice. All right. Cool. And then let me what did we say here? So let me switch, exit full screen, switch over to the homework. All right. No, those are the answers. That's not the homework. Okay, here's the homework. And then number 15, you say. 15. Yeah, your audio keeps cutting out. I hope that's okay. Hope mine's clear.
Yeah, you're okay. You're okay.
Okay. All right, so here it says a long solenoid, a long solenoid that has N equaling 400 turns per meter and is carrying a current given by this equation. Okay. Inside the solenoid is a coaxial, so that means they have the same, axis, with the coil that has a radius of 6 centimeters, and it consists of 250 turns of fine wire. What is the EMF induced in the coil by the changing current? All right. Now, there's always two steps to this. The first one is Faraday's Law, which is the magnitude of the calculation, and the second one is the Lenz's Law, which is the direction. All right, so I'm going to start with the Faraday's Law. It says the EMF, and I'll do magnitude of the EMF. That way I won't mess with the negative sign. I'll just put the number of turns is then equal to the derivative of the magnetic flux, which maybe I'll also then write the magnetic flux, because when you write it in terms of its calculus, you'll see that you have two steps of calculus, also involving vectors, dot product, but one is an integral over the surface area, so I call that an integral space, and the other one is a derivative of time. That's important here because, as you know, doing calculus, some of your parameters, some of your terms in your equations may be a constant, and that's where you have to be careful with that word constant. Is it a constant for all time and all space, or is it just a constant over space but changes with time? And so what is it? So we can have a constant in space but not in time, or a constant in time but not in space. All right. So with that in mind, let me keep going. So I'm trying to find the EMF inside the smaller one, I believe. Let me read it again. The long solenoid has 400 turns per meter. It carries a current of. Inside a solenoid is a coaxial with a coil that has this and the number of turns. What is the EMF in this coil? All right. So the coil itself has 250 turns, and so that's kind of that first step. What is N? All right. And that one's the pretty obvious one that, okay, it's just, this is what we get for one loop, then we multiply by 250, because we just wrapped it around 250 times. Okay, then I'm going to take this dot product, which is B times dA times cosine theta. And here's where I like to kind of pause and think about it. Okay, so for this coil, the field, the B part of this, is coming from the solenoid. And so I just want to make sure I use the right words here. So to distinguish the two, he calls the solenoid and a coil. I'll refer to the solenoid as the primary, and then the coil as the secondary, because it is the first one, the primary, if you will, the solenoid that is then going to have a current in it, which makes a field. If that it changes, then that will then induce a current and make a second field in the little coil. But
So, do you, for that B, is that just going to be using the solenoid equation we did 2 chapters ago?
Right. And so one thing you'll notice in this chapter is, in one sense, it is a short chapter. I was working, I believe it was Gina at the end of the last session, and I kept saying, okay, now here you do the right hand rule, and here you do, so and I was trying to point out that most of this chapter 31 really requires you to fully understand chapter 30. Okay? And nobody really does. So I kind of like the way the author has set it up. It's pretty clever in the sense that the author realizes that you do so much of chapter 30 here that anything you didn't quite completely fully understand, you get a chance to relearn it, if you will. Okay, so there's the 250. Now let's talk about the B field. As you said, where does it come from? Yes, it comes from the solenoid, which I'm going to call the primary there. And now I want to ask this question. Is it the same everywhere in space where I do the integral? Is it the same over time? And as you pointed out, and I'll just kind of write it off to the side, is back last chapter, we learned this equation for a solenoid. It's the mu naught times the turn density times the current. And one thing we did learn is everywhere inside of the solenoid, it has the same value. So because of that, here's what I would do is I would move the B field, and I'll even change my writing notation, but I will move it in front of the integral because it is the same or a constant in space. So I'll pull it in front of the integral. However, since the field comes from the current and that equation clearly has a time factor in it, it is not a constant in time. So I cannot pull it in front of the derivative of time. Although, as you can see, I can break it down into 3 factors, and 2 of those factors are a constant in time. And so I'll go mu naught times n, and then I'll have the derivative of I. So that's what I would do with the magnetic field. Now, the other thing I would do is back here with this dot product, I would go cosine theta. So again, another thing we learned in chapter 30 is that the magnetic field goes right down the, or parallel to the central axis. And the way this one is situated, the dA is that way. Or maybe if I kind of drew it this way, if this is the solenoid here, and it looks like they've got currents coming, I'll take it coming out of the bottom, meaning it would go in at the top. So they've got little X's in their diagram there and little dots there. So the current comes out, goes around, goes down behind.
Your screen froze.
Oh no. Okay, let me fix that. Reinitiated here, see what that does. All right, try our luck again here. All right, so I'm not exactly sure where it froze, but I was trying to draw, and I'll just draw 3 of them, that the solenoid has the current come out of the bottom and wrap around and go in at the top. And then, of course, the coil is inside here. And if I use the standard green color then, and again, this is, oh, now I've got a delay.
Yeah, I see that.
Put my hand here. 1,000, 2, 1,000, 3, 1,000, 4, 1,005, 1,006, 1,007, 8. Sheesh.
Wow.
Okay. I'm going to stop it again. It's been a little while since I rebooted my laptop. Although I didn't have any problems earlier today. But all right, gonna try to work through it here. But looking good right now. No delay. Good.
Yep.
Okay, so what I was trying to do here was to put my right hand in the screen and say, okay, I need to hold my right hand so the current comes out of the bottom and curls around to the top. And so what this would be saying is that as the current flows through here, this would be the direction of the flux. Now, I suppose also it's worth maybe drawing a graph of our equation as a function of time. But the equation they gave me was a 30 amps and then a 1 minus e to the let me zoom in. Is that a minus 1.6? Yeah. Minus 1.6 t. And so when t equals to 0, I've got 1 minus 1, which is 0. And of course, after a long period of time, e to this decaying exponential goes away, so I get 30 amps. So after a long period of time, it's 30 amps. And so clearly the transition from 0 to 30 amps is, well, let's see. If I read this, this is a decaying exponential that is upside down, shifted by 1. So it would go like that. So it would have this exponential decay, but upside down. Now, I only throw that in there because I'm not sure that I'm not sure I did a good job here focusing because I wanted to do direction and calculation, and I'm kind of mixing the two. But I did, so I maybe hold off on that. But what I was trying to do was get something about the direction of the field. And so the direction of the field is actually the same as the normal vector. So my angle here would be 0 degrees. And that's what I was trying to get at by drawing the flux. And then I started getting carried away in the direction of the flux. And so I apologize for that. I'll come back to this. Let me put page 1 here because we're definitely going to come back. We have to get direction. But I just, at this point, really just want to go through Faraday's law and calculate the magnitude. So this dot product actually comes out to be a simple calculation because, as we just said, the b we can pull out to the out of the integral, but not completely past the derivative of the current. And then the cosine of the angle is 0 degrees. That's really what I want to show you in this picture. And then I just have an integral of dA. And in that case, this then would just be the area, which I will write as pi r squared. And so this becomes then the area of that coil inside. And I think they gave the radius. Yeah, it has a radius of 6 centimeters. All right, so I'll continue on. And whoops, looks like I need a new yellow pad. Grab a new one here. Okay, and so copying, come back to my picture in a second, but copying this equation, I have 200 times mu naught here. Let me just write it as 4 pi times 10 to the negative 7. Then I have the number of, or the turn density. This is what's making the field. This is the 400 turns per meter. Then I have the derivative of the current, and that's a 30, 1 minus e to the minus 1.6 t. And then, of course, now just this area, which is pi times 0.06, let me double check, yeah, 6 centimeters squared. All right, and maybe before I take the derivative, I'll just also get out my calculator so I don't have to keep writing so many terms here, but this is the 250 turns that are in that secondary. Then times a 4 and times a pi and times 1 times 10 to the negative 7. Then times 400. Then times, and maybe I'll just leave the whole derivative alone. I was tempted to mess with the 30, but maybe it will be less confusing if I just leave that alone. And then this thing here, which I suppose I could put in front, and that's technically, I guess, what I am going to do. So times pi times 0.06 squared. And so all of that comes out to be 0.00142. And now I can do this derivative here. And of course, the 30 would be untouched. The derivative of a 1 would be 0. Then we got the negative, and the derivative of an e to the something is just e to that same something. And then the chain rule gives me a negative 1.6. And the two negatives cancel off, although not really important about the negatives because we started this problem with doing the absolute value and dropping the negative anyways. So whether those cancel or not, I'm just going to ignore them and call it a positive. And so now I'll get my calculator back. There's the number out in front. I can now multiply that by 30, and I can also multiply it by 1.6. So 0.0682, and then e to the minus 1.6 t. And that would be the EMF. And of course, it is a function of time. Do they say at what moment in time? What EMF is induced by the coil by the changing current? So I don't think we can answer anything better than that. We just have it as a function of time. They could have said, after 3 seconds or 1 second or at 0 time, but they didn't give me a particular time. They probably should have used the phrase, write the EMF as a function of time. But that would be the EMF as a function of time. Now, I can also continue and do direction here. This is where the Lenz's law comes in. This is why I started to draw the flux. Well, actually, I started to draw so I can get the angle. But then I got carried away, and I said, well, if this is with a flux when there's current, let's look at the current. So the key point of this graph on the current was to get you to realize that the current would start with 0 current and increase, 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 increase. Because the most important thing I can say about Lenz's law is that it opposes the change. It doesn't oppose the flux. Keep that in mind. It opposes the change in flux. So we want to really ask ourselves, how much flux do you have before the current started? Or before the event started that's part of this question. So I'd come back over here and say, well, before anything started, I had zero current. Okay. So that means I had zero flux through here, right? And so as the current increases, the current is going to make this flux that I'm trying to draw in green, and I'll call that the primary flux. Because Faraday's law says that the current in the secondary will be established so that the flux in the secondary opposes the change from the primary. So when you say oppose the change, that means go back to where it was. So I'm going to draw in blue a flux pointing from my left to my right. Because that blue flux combined with the green flux gives me my zero. And that's what it wants to be. It wants to be back to where it was. It opposes any change. So once I know the direction that the blue flux is, which is going to come from the current in the secondary, I can then go back to chapter 30 with my right hand and hold it so my thumb is in the direction of the blue flux, the secondary, and look at my fingers and see how my fingers then are saying that the current then would be coming kind of over the top and around. And so if you were actually standing on this side, looking at it, looks like you would see a counterclockwise. Now, since they don't say which direction we're standing and looking, I'm a little bit hesitant to write in counterclockwise. Because if I was standing over here, looking in, that would be clockwise. So I really think that they mean find the magnitude of the EMF induced, not the direction of it. Because, left to right or clockwise, counterclockwise, all these directions are all relative to where you're looking from. And I'll just kind of double.
I think it's okay to get the practice though, just to watch you do it.
Oh, okay, good. Yeah. So, yeah, thank you. Yeah, I'm glad I said it. However, I wanted to point that out because I bet now when I go to the solutions, they're going to just give me a number. Let's see. They write it this way, 68.2 millivolts. Good. Yeah. Oh, and they do say counterclockwise. Okay.
That's interesting. That's a little ambiguous, wouldn't it?
Yeah, I'm not sure you can say counterclockwise unless you also say that you are viewing it over here from the right, looking back. Did they? Huh. Okay. Well, yeah, I would say the answer could have done a little bit better, or the question could have done a little bit better if I say which side are you viewing it from. But anyways, I wanted to go through a direction, whether it was a good or poorly written question. It didn't really matter. Nice. All right, and let me jump back. You guys who came in a little bit later, you throw anything in the chat? No, I didn't see anything. Still early, probably still recovering from all the studying on the test. And so I wish I had gotten a little bit further. Been so busy this week, but both my classes took tests. So after I gave you guys this test and on Wednesday, I ended up helping them guys all day. And anyways, I still haven't made what I want to do tonight when I'm done with you guys. Or actually, I have that club meeting. I think I hope you saw that in the email. Yeah. So we're gonna cut a little short, and I gotta be on some panel, and hopefully I don't ask a question I can't answer or embarrass myself too much here. But but the video solutions I want to get to you guys while the test is at least somewhat still fresh in your mind. And so that's what I'll make first. So be on the lookout for that. I'll get the Zoom video and the video solution for that going tonight, and then maybe on tomorrow I can start grading that one. It usually takes me 2 or 3 days, so hopefully by Monday afternoon I'll have you guys a score for you. All right. Yes, dump trucks. They're loud. I was in a Zoom a moment ago, or well, not. Sorry, it was back when getting ready, trying to help students on Wednesday, and It wasn't a dump truck. What was it? It was one of these portable car washers pulled up for my neighbor outside right in front of my window, just blasting that thing with the power spray going and the compressor going. Like, oh, I don't know if I can hear you. So, now, if there's any, thing I want to say here is, and you saw this in the problem if you're following along, that you really got to go back to chapter 30 quite a bit here to do 31, because you got to get in this case, this one here, we had to get the magnetic field from a solenoid. We had to remember it was uniform. We had to remember it was related to the current, and then the current changed with time. So now we get into the 31 where we see something is changing with time. Because if nothing changes with time, Faraday's law, we don't get anything interesting. So from here and for the rest of the semester, everything's going to be more time dependent. And so it requires even more visualization than we were doing before. Okay, it changes with time. And then, of course, getting directions. I was constantly using my right hand here, saying, okay, clockwise, counterclockwise, thumb up, thumb down.
So, I still feel pretty shaky about chapter 30, if I'm being honest. I don't know really how I did on a lot of the magnetism stuff. But I definitely want to make sure that I'm not falling behind on here. So I wouldn't mind if there's a problem that you think in our problem set that you would want to go over that you think would help illustrate some of the concepts moving forward. I'd be down, or I could just throw out a number if to go over. I definitely am trying to aim for some exposure here, but don't want to try to get a general idea. So. Yeah, that's kind of where I'm at right now. I don't know if anyone else is in that same boat.
Yeah, good question here. I liked I really liked the one we just did. 15 was really good because it had the Faraday's law in it. It had the lenses law in it, but it also then brought us back to 30, and that's good.
The next question, number 16, does toroids. Covers toroids.
Yeah, that question was one of the questions was on that test about toroids.
Yeah. Oh, okay. Hey, that's a good one. How are we doing on time? All right. So I'll let me jump on to 16. See how that works out. I question your comment about toroid, though.
Yeah, that's fair. I haven't really looked into it. I just saw toroid somewhere. Toroid question.
Yeah, but this is a standard measuring device. Real good one here. It's got a fancy name, like a Rogetsky coil or something.
Yeah, that's it.
Yeah, it says Rogowski or whatever.
Yeah. Okay, there it is. Yeah, but I'm probably pronouncing it wrong, but Rogowski or something. Yeah, but nonetheless, Yeah, let's just get this one try. That's what you're asking for here. And so when a wire carries an AC current with a frequency, you can use a Rogaski or coil to determine the amplitude Imax of the current without disconnecting the wire to shunt the current through a meter. This is actually really, really nice. And as you see, it uses Faraday's law, so it only works when things are changing. So we are, by the way, about to enter a new, well, I shouldn't say a new phase, but like we did after 26, we did, we'll call it the applied chapters, 27 and 28, where we did circuits. We're about to do that same thing. But the next two chapters on circuits then are going to be circuits that change with time. So they might be DC currents that are turning on and ramping up, or turning off and ramping down, or they might be, well, if I could use this word a little early, AC currents where the current goes increases, decreases, increases, decreases, increases, decreases. And of course, an AC, we call that AC for alternating current, and it's changing all the time. And so you can use the properties of like Faraday's law, because Faraday's law only is useful if something changes. So you would not want to be messing with trying to use Faraday's law to measure the current if you just had the DC circuits that we did back in 28. That's not going to do you any good. But if it's an AC circuit, things are constantly changing. You may not actually need to disconnect the circuit. You may be able to figure out what the current is by the changing magnetic fields that are associated with the changing current. And that's the brilliance of this thing here. So let me see if I can describe it here. It says to determine the maximum currents, and so of course we're changing, so it's going to ramp up to some maximum and decrease, without disconnecting the wire to shunt, or that is to run it through the meter. The Rogowski coil shown in figure 16 simply clips around the wire. It consists of, and there it does say toroid, so okay. A toroid consists of a toroid conductor wrapped around a circular return coil or cord. Let n, little n, be the number of turns in the toroid per unit distance along it, so it's along a circle. Let A represent the cross-sectional area of the toroid. Let I as a function of time be, and then they give I max sine omega t, represent the current. Show that the amplitude of the EMF induced in this coil is given by this equation. Okay, so it takes a little 3 dimensions to see this. But if you look here, I think they're trying to show this bottom one as kind of a straight center. I don't know if I did this very well, but it looks like they've got it over the top, wrapping behind, over the top, wrapping behind, over. I'm going to turn up the magnification here. All right. Yeah, so they go over the top, behind, over the top, behind, over the top, behind. All right. But what they're trying to measure, and it might have looked like the center of the circle to you, is there's a circle with a dot that carries the current. And so all they're doing is putting this AC ammeter around this wire that is coming towards us. And this is why this one fits your question, Hunter, really well, because here I say, I'm going to say it, let's go back to chapter 30. All right. So chapter 30, we learned that the magnetic field from a long straight wire had these circles around it. We would take our right hand and we would put our thumb in the direction of the current. So in this case, I'm going to point it towards the video camera. And then my fingers would be the field. So let me call that the primary field, because I'm hoping you can then see, especially in this part of the drawing right here, that this field right here goes through these loops. And that's then where the Faraday's law comes into play. So let me write down Faraday's law. It says the EMF induced is equal to minus n being the number of turns in your inducted wires. I often like to call that the secondary. So this is the coil that we're using as our ammeter, our Rogowski coil. And then this is the derivative, the time derivative of the magnetic flux. Now, if you'll allow me, I will just say, let's find the magnitude of it. And I'll ignore the pluses and minuses. Or maybe I'll hold off on that. I'll leave the minus in here for a while. Why not? But we need a little more definitions to be real accurate with them. But as you see, we're going to see it goes plus, minus, plus, minus, plus, minus. So whether there's a minus sign or not, it's irrelevant. Okay. But the n is the number of turns. And in my drawing, it looks like I've drawn 1, 2, 3, 4. But they said little n was the number of turns per length. So I would have to multiply that by 2 pi, I'm going to call it r. Do they give me an R? To determine the amplitude, the current without disconnecting. So how did they define N? I want to be careful here. N represents the number of turns in the toroid per unit length. Okay, I'm going to call it R. And so say that this coil has a radius of R. That would be the number of turns. So here's the derivative. And then now I have the flux. And the flux is B dA cosine of the angle. And so N 2 pi R, here's the time derivative. And okay, now we have to say, all right, we're taking the flux through the coil. Now the coil is, again, wrapped around this center wire here. And so it's, you know, something like this. And so the flux actually comes from this long straight wire sticking out. So this is mu naught times I as a function of time over 2 pi r. But this would give me my chance to again say this is where chapter 30 comes into play. Chapter 30 says, okay, you know, what is the magnetic field from a long straight wire? So just like the number 15, I had to remember what does the magnetic field look like from a solenoid. Here I need to remember what does a magnetic field look like from a long straight wire. All right. And of course I have the dA, but the other part of chapter 30 is I have to know the direction of the field in relationship to the area. So again, coming back to this right-hand rule, I already drew it in this picture, but the arrowheads in green are pointing around in a counterclockwise direction. And for lack of other things, I'll use my power cord here on my laptop to say, look, my finger's right here, the flux is going through these little coils around here in the Rogolsky coil, okay? So those little areas would look kind of like little circles right here. I'll just make a circle. And so that would tell me that this angle is 0 degrees. So again, that's where we've got to go back to chapter 30. Before we can get the angle, we got to know, well, what direction is the field and what direction is the coil? And that's where that comes into play. And of course, cosine of 0 is just 1, so I'll drop it out of my equation. And then, of course, like all of our calculus, it's kind of nice to look at things like mu naught doesn't change with space, so I can pull it in front of this integral, but it also doesn't change with time, so I can pull it in front of the derivative. Now the current doesn't change in space, because it's the same all the way through the wire, but it does change with time. So I'm going to pull the current in front of the integral, but not in front of the derivative. The 2 pi r, I'm going to pull all the way out. I suppose I should be careful talking about the r. You might think that the r doesn't change with the space, but here's why they said it was a tight coil right here. And we are doing this integral within the loops of this tight coil. This is so tight, I can say that this loop is all roughly the same distance r away. So I would say, yes, this r is a constant over the area of this blue loop, only if this is really small and maybe this is really big. So, but I'm going to make that statement and see what they do in the answers. But I think they do that so we can cross that out. And then, of course, you're just left with the integral of dA, which is then the area of this little coil. And then you have the derivative with respect to time. And I think I don't quite got it. I was going to say, I think we're done, but they gave us then that the current can be written as a maximum current times the sine of omega t. So when I take the derivative of that, I would get I maximum. Derivative of sine is cosine omega t, and the chain rule is an omega. And this is, of course, the EMF. This is the part that I was saying then. After you go through all this math, you'll see that the EMF, it changes with time. But if the last step would be to say, well, what's its maximum? And remembering from our trig class, this would go up and down. The cosine function would go up to a maximum of 1 and down to a negative of 1. So this thing out here is as big as it ever gets. This is the maximum. And so there is, ta-da, the answer.
Awesome. Thank you so much.
And
I think we're about out of time, right?
Yeah, and I apologize for a little bit of shortness if you want me to make something up somehow, but given we're starting a new unit, it's week we can work on some things or something. So I know that two of you can only kind of pop in here after the 3 o'clock hour. So
yeah. No, totally good. Thanks for making the time and also making the request for a not clear answer or question. Awesome.
all right, guys. I need to bug out for my next meeting, but yep, let's keep asking questions. We've got another 5 weeks to start learning this stuff.
All right. Thank you
Good
very
one.
much.
Thank
Bye
you.
now.
See you later.